2025 OCR paper, people. Nah, it's not really. Does the 5 look terrible? Now, there's an old wives' tale that I'm going to want you to see if it works for me. Now, just so you know a bit about me, I was a teacher for 10 years, I'm an examiner, and just so you know, I run a tutoring business now. Now, what the old wives' tale is that apparently every 3 years, everything in the syllabus has to come up. So what that means is if it didn't come up in 2023 and 2024, there's a high likelihood that these topics should come up. So as you can see, the ones that are going to potentially come up are network security, protocols and threats, operating systems, database concepts, legal and ethical issues, particularly focusing on the Data Protection Act and Computer Misuse Act. And then we've got Boolean algebra, logic simplification with K-maps, okay, Karnaugh maps, okay. Now this is a little extra to the old wives' tale, but if we also look at the past papers, there's some frequently assessed topics. These are the ones. So we've got processor architecture, data representation, particularly floating point normalization, things like that, the software development life cycle, and assembly language. Because I don't think we should ignore these, because if we look at the past papers, these come up all the time. Now what we're going to do for the rest of the video is I'm going to go through all of these different topics in various different ways by putting up predicted past paper questions, and what I want you to do is make flashcards, watch the video, engage with it. That's what's going to help you get those top marks. If this has been useful, please like and subscribe, people. It helps me know that I'm actually helping you guys and that I'm not just talking to myself. Anyway, let's get into it. Basic instructions. We're just going to add two numbers together. First thing, I'm going to input in a number, INP. And then what I'm going to do is I'm going to store this in A. Store is STA. You can actually use STO as well, but STA. And then I put the variable that I want to store, which is, I've just called it A. I could call that whatever I wanted, num1, num2, whatever you want to call it. I input in a second number. The next line is going to be to add A, and then output this, and then I'm going to stop the program, and I declare my variable at the end. This is a von Neumann architecture where instructions and data are stored in the same place. So what we need to do is we need to make sure we have enough space whilst when we're creating this program. Works very, very differently to high-level languages, which is where we store things at the start of the program and initialize our variables. We initialize them at the end. We can then click submit. I'm only going to do it slow once so that you can see an example, and it is showing you the fetch, decode, execute cycle. It's fetched an instruction, and now it's going to tell me to input a number. Let's say that I do 10, and I'm going to add 5 to it. So we store that in the accumulator ready to be used, and what it's going to do is store that in position 6, which is the 7th, because obviously it starts from 0, 0, 1, 2, 3, 4, 5, 6 is 7, and you can see that 10 is going to position 6, so that's where it gets stored there. If you're looking at all of this and you're just like, this is just a load of colors moving around, do not worry. All you need to know is this block of code here what it does is it adds two numbers together. The visual representation, you haven't got that in the exam. Don't worry about it. It's start thinking to yourself, this is where you could maybe grab a couple of marks. If it's a really complicated piece of code, and the only thing you can remember how to do is add two numbers together, just write it down. Remember this, make a flashcard of it and say to yourself, this code here adds two numbers together. You never know, you might grab yourself a mark or two. So use it. Anyway, arithmetic logic unit adds the 10 and the 5 together. And then what it's going to do is it's going to put the 15 up here. Goes and fetches that. As you can see, it does take a little while though, doesn't it? And then 15 goes up there. Program is going to stop in a second. So first program, adding two numbers together. Make a flashcard, practice it until you can remember it off by heart. I'm going to stop that because the program is simply just going to stop. The next program we're going to have a little look at together is we're going to look at how to hard code. Actually, first of all, the two arithmetic operations you can do with this style of assembly language is subtracting and adding. So sub is subtract, add is add. So that's the next one. Another thing which is quite important is being able to
hard code values into variables. So let's say that I wanted to hard code the number 1 into 1. So I put dat 1 and I hard code the value that I want to go in there. So because I've hard coded that, what that's going to do is that is going to that's 1 is going to be placed into this variable. I then, if I wanted to, let's say, input a number, subtract 1 from it, and then output it, I input 10, I subtract 1 from it, and it gives me 9. I have no idea why you would want to do that, but let's say it does. And then it's just going to do that, and it goes through, so 10, and as you'll see, it outputs 9. Okay, so again, that's how to hard code a value in there. So that's kind of another skill to your arsenal. So again, make another flashcard. How do we hard code values in there? Now, next part, one of the most important things that you need to be able to do in assembly language is make sure that you have the correct variable in the accumulator. The accumulator is where all decisions are made. So when we get onto BRP, BRZ, BRA, if you don't have the correct variable in the accumulator, it isn't going to make the correct decisions. So I know this sounds confusing, but it's important that we load the correct ones in there and the correct things happen at those moments. So if we wanted to load a value into the accumulator, this is how we do it. Let's say the program is that we want to input 2 numbers. Now at this moment, the B is in the accumulator. But let's say for whatever reason I actually want to output A to start with. I put LDA, which is load A, and I output it. I LDA B, and then I output that. And then what I'm going to do is stop the program, and I just declare my 2 variables. Write it into yours. You can see mine's assembled all correctly. Try it out. Another thing that you can do, and this is, try and extending those programs. So maybe input 5 numbers and try and output them in all kinds of different orders. So start with the second number and output that first, and then the 5th, and then the 3rd, and just go in different orders, because that's going to build your understanding of how actually this LDA works. And once you understand that, I think that's probably one of the big things that I see people just not understanding, and then they can't answer any assembly code questions at all, is that they don't understand how to get the correct variable into the accumulator. And as soon as you can do that, then we can access some of the more difficult questions. Now, I know I'm trying to go through this as quick as possible for you, so just stay with me, keep writing the programs. What I want you to do now is we're going to go for a countdown program. So let's say I enter in the number 5. And what I wanted it to do is output 5, 4, 3, 2, 1, and then stop. And we're going to use a combination of BRZ, branch if 0. So if the count equals 0, we want to stop the program. And then otherwise, we want to keep doing what we're doing. And we can use BRZ and BRA together to create almost like a loop, a while loop, a conditional loop. So let's have a look at how we do that. Input in a number. First thing is store it. We then output this number. We are then going to subtract 1 away from it. And this is where we do our check. BRZ end. We want it to, so you put a label. And what happens is that is then going to jump to a point at where we also write end on the left-hand side of the program. I'll show you what that looks like in a second, but it runs a check and says, is the number in the accumulator 0? If it isn't, it's just going to ignore it and go on to the next one, which is BRA, branch of always, and we want this to loop back up to the top. We join the loops, join the labels, and we say, we want you to jump back up to here if your condition is true, which it will always be true if it gets there. So that's why you put the BRA afterwards, because it's going to do the check first. If that isn't true, it just ignores it, goes onto that one and jumps back up to the top. And then if it is 0, what we want to happen is end, HLT, stop the program. And then we're just going to declare our variables, so ADAT, and then we just need to hard code 1 in there. And as you can see, let's just quickly run this. I'll do it on the quickest mode for you because I don't want to waste your time. So if I enter in 5, it's going to go 4, 3, 2, 1. Hard code, so you code this now, write, draw on it, what is doing what. Make sure that you fully understand each stage. And that is probably one of the most important structures that you need to be able to get, that this idea of being able to create a loop, jump around the program. Message me if there's things that aren't making sense. An extension question on this that I would recommend having a go at is trying to have a look at BRP, which is branch if positive, which actually I think it also accounts for 0 as well. But try with that program, if you input 2 numbers and you take one away from the other, output the larger of the 2. So think about how that one might work and see how you get on. So with this one on here, what we're now going to do is do one of the more complicated programs, which doing one of the more complicated programs is we're going to actually have a go at doing multiplication. Now, without the function of multiplication, if we have to break this down into the bare bones, which is essentially multiplication is where we add a number repeatedly to a total until a set number of times. So 3 times 2 is we add 3 to a total 3 twice, and that then gives us 6. So what we are going to do is we're actually going to use this countdown program to help us. So let's have a look at how we do that. We're going to input a number and we're going to store it in A. I input another number, store that in B. I'm then going to load total, which is 0. And I'm going to add the first number onto it, so add A. And then what I'm going to do is, so I load the total, add A. And then what I'm going to do is I need to store that in total. One of the big things I see from the examiner end is that people don't seem to understand that when you change something in the assembly language and then it doesn't automatically save the change. And so that works in both ways, is that people don't realize that that number hasn't been saved. Also, they don't realize that for them to save it, they need to say store that total. So that's a really, really important part there. Make sure that you do that. So we store that in total. So 0 becomes 3. And then what we need to do is we need to deduct 1 from the second value, so which is going to be 2. So we're going to load B, sub 1 from it, and then store that again. Remember, we need to change the value, so we store that, overwrite it over the top. Then we're going to store B, and then we are going to then do our checks. So we need to go BRZ end. If it's 0, if B equals 0, then it's going to stop the program. Branch if always, so our conditional statement, we want to loop back up to the top where we want to go to just the other side of total here. We want it to jump back up to there. Otherwise, we're going to want to run like our end procedure, which is where we load total, output it, and stop the program. And then I just need to initialize my variables, which is ADAT, BDAT, total, DAT. I guess you could set it to 0, but it doesn't really matter. It automatically does that. And then you've got 1 DAT. 1. And if you have a look here, this should, so it's initialized all okay there. Let me run this really, really quickly, just with 3 times 2 so you can see it working. There you go. So extension problem, if you want to have a go at this, is how do you do division? Division without the use of a function is where what we do is we continually subtract a number away from another number. Do integer division, don't bother doing decimals. To repeatedly keep subtracting a number away from it and counting how many times until you get to 0. So that would be sort of a bit more of a challenge on that one if you want to give that one a go and let me know how you get on. So what we've got here is we've got another, and I think it's the last one on there, which is a 9 marker, which is all to do with essentially talking about the different stages of the software development life cycle, and it's a 9 marker. So we can see that it's really important that we get this strategy of how going through and writing in, describing what it's talking about, and then applying it to the scenario. So the scenario is that a client is going to try and create a complex computer system, and they want to compare the spiral model and the waterfall model. So the essentially what it says is how both methodologies could be used to develop a complex computer system. So obviously functional, the benefits of each methodology for this task, the drawbacks for each methodology for this task. So we're just going to go through each of those. So again, the first paragraph is going to be so important just to outline that you actually understand what each of those things are. So I'm just going to make some points about waterfall. So the waterfall model is where you have the different stages, and if you can remember all of them, that's obviously going to be great. So think about your NEA, analysis, design, programming, evaluation, and testing. And what the model does is it starts at the top of the waterfall analysis, and in a linear fashion goes through each of the different stages. So I'm just going to outline that I know what the waterfall model is, and then what I'm going to do is I'm going to talk about the spiral model. The spiral model is has the same stages, but makes use of prototypes throughout development. So what might happen is is in development is you might go through 3 or more iterations of each stage of the software development life cycle to keep refining the project through getting feedback after you have finished a prototype. Okay, so I've just outlined what each of them are. Now, in a complex model, now we need to start applying this and evaluating it and saying about why something's going to be good, why something's going to be bad. So one of the big benefits of a waterfall model is the waterfall model is really good if the program that we are making is easily understood and has been completed lots of times. For example, a complex computer program could mean building a website. If this company that was employing this model, I don't think employing is the right word, that was using this model, had completed similar projects before, it is going to be the most cost effective. And then what I would do is then I would link this to the spiral model, but I'd maybe make a negative point about it. Spiral model is for businesses where it is going to cost a significant amount of money, as you have to make multiple prototypes. And also the development time is going to be a lot longer than if you used waterfall. It's getting a little bit weird there. I'll move it over here. Okay, use waterfall. Okay, so it's going to be a lot like that. If I'm honest, I'd probably go for another advantage and disadvantage, so I'd go for an advantage of a spiral. It has said
that it is a complex problem. So as the benefit, or the main benefit of Spiral, is that it takes longer, which isn't a benefit, but takes longer, but it gets it closer to the user's requirements through prototypes and asking the user how to improve each prototype. The waterfall model, you cannot go back up the waterfall. So this may lead to making a program that isn't what the user wants. So if it's a really complex program, so again, it's just essentially there's no right or wrong answers in these ones. I think generally they're trying to say like that what you want to do is you want to go for the spiral model, and talk about how the spiral model could be used because it's a complex problem, and just talking about how development time is going to be longer, it's going to cost a lot more money. But one of the big benefits of this is because you're making prototypes throughout and you are constantly talking to the user and saying, this is, how do we, what's going to be the things that we can do to improve this prototype? And because you do the iterations going through each stage over and over again, you trade off the development time and cost so that you actually get it closer. And that's if it's a complex program like that. So I think that's obviously what the question is asking us to do there. But just make sure that you're going with that strategy of define what the waterfall model is, define what the spiral model is, and then just make some good points about it, because the waterfall model does have some benefits. It's a very simple model to follow. It's if it's a website that they've made before, it's probably just going to be that they can just use a template that they've done before and change it to fit the user's requirements. So again, that would be something that I'd be talking about in there. But trying to make at least 2 advantages and 2 disadvantages. If you've got 9 minutes, I would say give yourself 9 minutes on this, 10 minutes on this. If you're going way over that, stop, finish the rest of the paper, come back to it so that then you don't go over in the actual time. Okay, right, unit 6. So question 6, I should say. So let's have a little look. So we've got multitasking operating system. She has access to a printer. Broadband internet connection through wireless connection. The operating system uses scheduling algorithms such as first come, first serve, and round robin. Okay, explain why a computer's operating system uses a first come, first serve when sending documents to a printer. So this is going to be for the printer queue, and everything has equal priority when going to printer. So essentially it's this idea that when we send something to the printer, things generally don't have priority over others to be printed first, unless it was some kind of strange situation. It's just whatever gets there first, we need to print it off. So what we would do is we'd implement essentially what's called a FIFO data structure, first in, first out. If it's first there, we're going to take it out of the queue, print it, and then on to the next one. Explain why the computer's operating system uses a round robin for allocating processor time. Again, quite a tricky one, this one, because essentially it's 3 marks. I think people will maybe be able to get a mark on this, but yeah, no, it's quite hard with the round robin. So explaining in this particular situation, so round robin is the concept of where we give a time slice to each job, and if we finish it in that time, great, we move on to the next task. But if we don't, then what happens is then we go on to the next one, onto the next thing, so to make sure that everything is fair. Now, in terms of processor time, this is a good way of making sure that fairness is ensured. So we kind of need to get this in there and explain like why we think this is. So this allows for, I think the buzzword they're going to be looking for. So this allows for multitasking.
multitasking, which if you know, I always talk about how important it is for the buzzwords in there. So like you need to make sure that you've got those ones in there. Multitasking, if that's not there, they won't give you a mark for that bullet point. There's multiple ones that you can use, but that's going to be really important in there. So it's going to be, I would then go into the point. It gives a time slice to each process, and will work on for that period of time, and then if it finishes, the task moves on to the next task. If not, if the time runs out, we'll move on to the next task, and then puts the task it didn't finish to the back of the queue. Okay, and I think it's just to really talk about how the processor is going to use this to essentially efficiently go through all of these, and talk about how it's really important that it does these things as efficiently as possible. Okay, and then it just says describe another scheduling algorithm in there. So we've got the one that I would probably go for. Well, there's multiple ones you could do. Which one did it said in there? So it said first come first serve, round robin. So we've got shortest job first, and then we've got short, which is probably going to be the easiest one. So shortest job first. The job with the shortest amount of time is going to be is processed first, which is just that nice easy one for there. You get a point for that one, point for that one. Okay. Now we're going to have a quick look at these ones, which is talking about the TCP IP stack. It says explain what happens at the application layer of the TCP IP stack when using this program. Okay, so and we use an encrypted messaging program to communicate with our friends. The computer uses the TCP IP stack, and it's a 5-mark question. So at the application when using this program. Okay, so this is where we need to be talking about. So it's talking about messaging, and we need to obviously relate it to the scenario there, but we need to be thinking about the stack, protocols that are going to be using. So this is what I'm thinking about in my head. Protocols that are going to be used if I'm going to be passing the information down to the transport layer, because we're going from application to transport layer, and how that's going to operate. So yeah, let's have a think about that. So the application layer is where the messaging program is going to be used to send the messages. If this is an email, we'll be using SMTP to send the emails from there. So I'll be talk about that. I mean, it's not too clear about whether it's emails and what's going to be going on there. But the other things that I will be doing that will be helping me to get marks potentially in there is talking about how the application layer passes down the data to the transport layer, and thinking about the stack in the order in which these things are in there. So the application layer passes down the data that is going to be sent to the transport layer. Okay. So to get the final marks on this, what I'd be saying is, because it says this is just what happens in the application layer when using this program, so it's not actually like sending all the time. What it's going to be is it's going to be also receiving. So we can also get the marks as well. This is the thing that I always tell my students. So what I'd be thinking about in this is that in the TCP/IP protocol stack, essentially what you've got is you've got the application layer. I'll just put app. Then you've got the transport layer. I'm going to type this because I'm clearly not doing very well on that. Then you've got the internet or internet layer, internet layer or network layer, whatever you call it, and then link layer. I know they're different. Sometimes people call it different things. So you've got the different layers. So you've got the application transport. And this is essentially here, what I'm going to be talking about is I'm going to be thinking about which layer is the layer it's talking about touching. So it's touching the transport layer, so it passes things down to the transport layer, but also when it's receiving data, it takes data from it. The other thing as well, which I know sounds a little bit obvious, you can also actually pick up a couple of marks here for just saying this is the layer where it encrypts it, and then I'll maybe put in there HTTPS. So if they're doing anything to do with that, that's what's going to be doing this. Also, because it receives it, it decrypts it. If it's received an encrypted message from somewhere, and also decrypts message. The other thing as well to get the final mark on there is I'll talk about how it receives the data from the transport layer. So that's another thing. So this one I always see students really struggle on. It's just think about the layers. So the first thing I'm thinking about is protocols. What protocols operate at which individual layer? Then also what I'm going to be doing is where am I going to be receiving the data from? So explain what happens at the link layer, sometimes referred to as network interface layer, network access layer, or simply the network layer. Of the TCP, I've actually heard the internet layer also referred to the network layer, so that's really confusing. Of the TCP IP stack when using the protocol. So when using this program, sorry. So the link layer again, so it's 2 marks here, so it's going to be receiving data from the internet layer. It's going to be also this is the one where it if it sending data, it attaches MAC addresses on, and then you can do the inverse of it. So it receives data from literally from the internet. It's going to take off the MAC addresses and then pass it up to the internet layer. So you can do it the other way around as well if there are more marks there. And then essentially, all we've got. That's actually going to be it. Okay, so that's the end of the paper, people. So I hope you found that useful. Please do give it a little comment if that was really useful for you. And I'll keep making more of these. So thank you very much, people. Gate that we need to know is the NOT gate. Now you will remember a lot of this from GCSE, but the thing that you will not know is the Boolean notation, which is what you are expected to know for the Boolean algebra. Now OCR has a slightly different Boolean algebra that it uses from AQA and Cambridge International. To do not A, you need to put a little, it looks like a fallen over L, okay, so a fallen over capital L. And like that. The truth table's here. I'd get all of this information down, I'd put it on a flashcard, and then you can study it. An AND gate, remember AND, have to remember what this one looks like. It's A, N, and then it's like the D on the end of it. Obviously it's a capital D. Now, again, the thing that you will not be familiar from GCSE, if you didn't do GCSE, get all of this information down, but the Boolean algebra that you won't be familiar with is this. And what it is, it's like an N. Okay, so that's how I remember it. It's like the A in A. It's like the N in AND. So that's how you write it, A and B, because those are the 2 inputs going in there, and that's the output. Or, the way that I remember the OR is because it curves in at the back. It's like you can write the O in the OR at the back. Now with this, it's the N from the AND gate is flipped over. So you just flip it over and it's like a V. Okay, so that's how you do A or B. And this is all of the information that you need for this one. For creating different logic circuits, so these kind of questions do come up. I'm going to give you a little tactic for it. If they've got logic circuits where they've got multiple gates, this is how I would do it. So you take in the inputs, and the truth table essentially is all of the possible inputs and what could be all of the possible outputs. So you've got 0 or and 0 because it's going into an AND gate to start with. And then we've got an output of R. And this is perfect in the way that it's set up. Because what we're going to do is we're going to work with R. Do not try and do the whole thing. Split it up into different areas. And then what you do is you just go through the different sections. So here we've got 0 and 0. So the truth table for that is going to be 0. 0 and 1. So remember that's going to be 0. 1 and 0, 0. And then that's going to be a 1. Then we take the output here and then it goes into a NOT gate, so it's just going to be reversed, so it's going to be 1 1 1 0. And that is probably one of the most important things in your truth tables. You need to put different sections for the different AND gates, for all of the different OR gates, NOT gates, and then split it up and treat them individually, and then you get to the end of it. Don't try and do it all at once. So with all of that, that is then going to take us to a situation where, you know, we can start creating them together, and then we've got the Boolean notation for it down here. So we've got A and B, and then all of that goes into an OR gate. But one of the things that we are going to want to do is have a quick look at the XOR gate, which is, with the XOR gate, this is one of the gates which you probably won't be familiar from GCSE unless you've done the Cambridge International Specification. With this, what's going to happen is it works in terms of exclusively OR. So you know with an OR gate it's one or the other or both of them. Exclusively OR essentially works with 0 or 1, but not both at the same time. And the Boolean notation for this is the OR symbol, but a line underneath it. And that's what the XOR gate or XOR gate is how you do that one. Now, what we're going to do is, in a new section, is we're going to get down all of the rules for Boolean algebra and how to simplify this. To give you an idea of why that we use Boolean algebra and why this is different, is there was a person called De Morgan who came up with this concept of how to simplify logic circuits. And the idea behind this, of why we want to simplify this, is because if the logic gates or logic circuits are more simple, then it's going to be less manufacturing costs and they're going to work more efficiently. So those are the two main advantages, and that could be a little 2-mark question that you could get there. Now, with the first law, one of the first ones is that not A or B is equal to not A and not B. That will feel, if this is the first time you've looked at this, you're probably thinking to yourself, why is it that I need to know that? Now, in certain situations, it's going to be more beneficial for you to swap that into that. And then in certain situations, it's going to be more beneficial for you to go that into that. And this is just a truth table to prove that this actually does work. So as you can see, that you get the same output even though you apply it completely different gates to it, and you can swap them. They're both interchangeable between each other. So that's something that we need to do, because in certain situations it might be beneficial to do this, certain situations it's going to be beneficial to do this. Now, if we look at the second law, not A and B is equal to not A and B is equal to not A or B. So again, there's the truth tables underneath it, and you can use those interchangeably because certain situations it's going to be better for you to do those. Now, these are kind of I think there's 17 different rules, so there's a lot of them. And what you just need to do is you just need to practice these lots of times. I would just spend time, all it needs is 10 minutes, a couple of times a day for the next few days, where you just write them out, see if you can remember them. If you can't, the ones that you can't remember, cover them up, write them out again until you can remember them in your head. Now, with this one, so let's go through why these work and why they are doing it, because I think if you understand why, that makes things a little bit more easier for your brain to remember. So you've got X and 0. So if we think about how an AND gate works, both of them have to be 1, don't they, for us to get an output of 1. Now in this case, if we've got 1 0, it doesn't matter whether that's a 1 or a 0, it will always output as 0. For this one here, it's X and 1. So whatever x is, if it's a 0, it's going to be 0. If it's a 1, it's going to be a 1. So it's just going to be x. So we can get rid of that 1 there. So again, we're trying to reduce the number of gates or number of inputs that we've got there to make the logic circuit more simplified. X and x. If x is 0, it's going to be 0. If x is 1, it's going to be 1. So it's got that there. X and not x is going to simplify to 0, because whatever x is, we're always going to create a situation where there is going to be 1 or a 0, because if x is 1, then that's going to be 0. So we are never going to get a situation with 2 1s. So then that will always simplify to 0. Then we're going to go into the OR gate. So x or 0 is x. The reason for this is because if x is 1 or x is 0, that is just going to be whatever x is, because we only need 1 1 in an OR gate for it to be a 1 overall. So whatever x is going to be that. X or 1 is going to simplify to 1, because we've got a situation where there is 1 1. An OR gate only needs 1 1, so that's why that would simplify to a 1, because whatever x is just going to simplify to there. And then x or x is just going to simplify to x, because if it's a 0, it would go to a 0, or 1, it would simplify to a 1. X or not x, this would actually flip round, and this would be a 1 in comparison to the same situation in an AND gate, because we're always going to create a situation where there is at least 1 1. And with an OR gate, if we create a situation where there is at least 1 1, that's what's going to happen there. And then not x is the same as x. Now if we think about that, because the double not there, what that would do is that would reverse it twice, so it just gets you back to the initial value. So it would, if not x is 0, not x is 1, and then take the not off again, then that would be a 0 again. So it just takes you back to the start. So you can take the double not off. There's still 2 after this, because we've got the absorption rule as well. But commutative, essentially it just means that you can just swap them around. It doesn't really matter which way around it is. So x and y is equal to y and x. Which, that kind of makes sense. If we think about the laws of the way I see it, and is almost like timesing, and OR is adding. So if you think about it in that, 2 plus 3 is equal to 3 plus 2. So there's that in there. Associative, where essentially that's a similar sort of situation where if you've got x and then in brackets you've got y and z, can you see that we've swapped the x into there? Because the gates are the same, you can just swap them in. And then here you've got the ORs, and then you can swap those in there. So as long as the gates are all the same, you can swap the letters in, and it might be more beneficial for you to swap those in that particular circumstance. Distributive is almost like expanding brackets. That's the way that I think about it. So if you look here, if you add a value on the outside of the brackets, what you would do is you do x times y, which will give you x times y, x times z gives you x times z, but you've got an OR gate in the middle. And this is like expanding double brackets. So as you can see here, you've got expanding double brackets, and you just go through each. X times w gives you x times w, x times z gives you x times z, and then so on, and then you times the y's. So those are the ways, little heuristics that you can use to help you with trying to work out what those are. Absorption rule, this is just pattern recognition. Pattern recognition is probably the easiest way to actually know this one. With this, what you've got is you've got x or, and then if the gates are swapped around, so if it doesn't matter whether it's an and then an or an or then an and then an or, and you've got 2 values which are exactly the same, one on the outside of the brackets, one in the inside of the brackets, they simplify down to the one where you've got two of the values for. So you can see here that they simplify down to x. All I would say to make this easy for yourself is just learn that pattern that you're looking for. So the gates are different, and then different in the ways of and or don't include XOR in that one. So and or are going to be different. And then the other condition that you need as well is that they've got 2 inputs which are the same, so 2 x's or 2 y's or 2 whatever it is, and then it simplifies down to that. Okay. The last thing that we need to do, and this only comes with practice, is you will just do more of these questions, and you'll start to notice that they follow a particular trend. If I'm honest with you, in OCR they tend to use the Karnaugh maps, which I'm going to do a lesson about next week, how that all works. But essentially with these, what you need to do is you need to just look at the patterns at which we can use to simplify them. So can you see here we've obviously got A or B and then A or C in there. So we use the distributive rule, which is like expanding the bracket. So B times A gives us B times A, and then we've got B times C gives us that. Now here, if we relate it back to the absorption rule, we've got a situation where A or the gates are different, and then what happens is we've got two letters which are the same. So that can just simplify down just to A, and now we've, as you can see, we've actually cut it down so that we've got less input, so that the circuit is way more simplified. This was actually a question from, I think it was the 2021 November paper that I just wanted to show you the rough level at which it's required of you. So it just says simplify this expression, try and show that so that it doesn't show any negation. And it's a 2-mark question. It's not crazy hard, but I mean, obviously if it's the first time you've seen it, this will look quite alien, but let's just talk about the steps. So expand the bracket, think about it like that. So you've times in the knot, so you've got a double knot, and then you've got a double knot on B. Now, if we relate that to one of the rules that we've got, which the double knot, can't we take that off to just equals X? Obviously, we can just take them off, so it's just going to be A and A or B. Sorry. So it's just about noticing those patterns, and as I said, I know that if this is the first time that you've seen it, this will be feeling a bit horrible, but just keep trying with it, keep doing lots of questions, and you will start to notice little patterns. The ones which I've seen quite a lot of, so I'm just going to put some different examples on, and if you cannot find any more questions, obviously message me and I'll get some questions over to you. Even use these ones, so just, try writing them one time, and then the next day, because your brain will probably have forgotten them, try writing them again, see if you can practice the steps in there. They seem to use the distributive rule quite a lot. So the distributive rule is that multiplying brackets. Is it a guarantee that they're going to use it? Well, no, because as you saw in the last question, they didn't use it, did they? But I just see that one come up quite a lot. And then they seem to always use they sometimes use the absorption rule. So it's about noticing those little trends and patterns that the examiners seem to pick. So yeah, here you can see that I've used the distributive rule to expand the brackets here, and then essentially what we've done here is we've got which this one may be a little bit more difficult to see. They've used rule 7, which is X or X is equal to X. Well, can you see here how they've done that? They've actually cut out one of the brackets, completely cut out one of the brackets there. So you've got X and Y or X and Y, and that's simplified actually down to X and Y, because even though there's two values in there, they're still exactly the same. So you've just cut them down from 2 to 1. And then here's a couple more examples there that I just thought that you could practice with. Again, the way that I would practice with this is just write them down, have a look at them and be like, okay, yeah, they've used the distributive rule there. Here they've used rule 4. Here they've used rule 5. And then later on in the day, try and see if you can remember the steps and look at them and see which ones, see how far you can get with trying to remember it, and then try it the next day. And what it is all to do with is simplifying Boolean algebraic expressions. So the general steps of what we need to do is being able to put inputs and outputs into 2, 3, and 4 Karnaugh maps where they've taken various different inputs in there. And then what we need to do is be able to actually read Karnaugh maps to see how we can simplify them. So let's have a little look at what we need to do on these ones. So comparing this to a truth table, you can see that we've got the truth table over here and how the outputs correspond to the different positions in the Karnaugh map. So this is the Karnaugh map over here. You've got the inputs here, and then you can see that these are the outputs and how they correspond to a specific place. So if we take a XOR gate, this is how it would look in a Karnaugh map, and it's just slightly different in that way. So what I've done is I've put the OCR Boolean algebra there and the Cambridge International Specification ones over there because they're slightly different from one another and how they display them, so that you've got them both there. So with your respective exam board, just look at the correct one. Okay, so we've got two inputs. We've got A and B, as you can see here, and what we're going to do is we're going to look at how we can actually register this information in there and put in the outputs in the correct place. So what we need to do is, first of all, we're going to write a 1 in each of the places where A is true. So as we go down to where A is on, so true, and that we're going to just write 1s in each of those. So we're just looking at this part here first. We're then going to take the second part of it, which is going to be the A and B, and because that's in brackets, we have to take them both together, A and B. And then what we're going to do is just put a 1 in where that is true, and there is only one place where that is true, which is there. So as you can see, it's already been filled in, but just to illustrate the point, that's what we're going to go for. Then what you're going to do is draw a box around it, so we draw a box around it, and then we think to ourselves, what is the value which is not changing? So in this case, A never changes from being true. B changes because, as we can see, B goes from 0 to 1. We don't use not A at all. So in this case, we can simplify this just down to A, which, if you remember from the Boolean algebra lesson, this actually matches the absorption rule. So as you can see, this is just going to simplify to A. Now, one of the skills that I see a lot of my students struggling with is when it's on there, what is it actually telling us? So, if that didn't make a lot of sense there as to why that was A, the reason is because A, so when is because it's a 1 there, never changes from that. So that's why it simplifies from there. All of the other values change. So from here to here, B changes from 0 to 1, so it's not going to be any of the B's. It's not going to be not B or just B there. Or here it's not in the not A column, which is 0. So let's have a look at a couple of different combinations. So if it was just not B in here, if I draw a little shaded area around this one, so you can see that B changes just so it always stays in the 0 column for B. So this would actually simplify to not B. This one here, so it would be not A because it stays as 0. So it's always going to be not A. So in this case, that would be a good indicator that it would be not A. And if there was a 1 and a 1 in this one, that would just be B because B stays the same. And it's all about consistency with this. Now, that's kind of the first technique on this one. So to be able to put values in there and then just be able to actually read, like, what has it been simplified to? So those are the two skills that you need to be aware of, is like putting the values in there and then also being able to read it and simplify it. Making it a little bit more difficult now is a 3-variable Karnaugh map. So with a 3-variable Karnaugh map, what we've got is you lay it out like this. So you put one value down here, and then up at the top, you're going to put 0, 0, 0, 1. Confusingly, you put 1, 1 there. So just remember that one. So you're actually going to put the 3 there, not the 2, and then you put the 2 in. Okay, so that's just a really important point there. Now, if we have a look at how we would actually represent these particular values in there, what we have to do, so this is the Cambridge, so we've got A and not B, A and not B, or C, So that's the OCR variation. This is the Cambridge one up here. Now, first of all, what we're going to do is we're going to take the part which is in the brackets, which is going to be A and not B, and we're just going to deal with that part first. So all we need to do is we just need to put we need to put 1s in where this is true. So we put them in this one here, because if you see where it's A and not B, so A needs to be 1 and B needs to be 0. So the only situations where that is true is going to be in this box here, because don't ignore the C. We're not going to worry about that. We're just dealing with the parts in the bracket. So it's going to be A and not B, A and not B. The reason we don't put it in here is because B is going to be 1 up here, so that isn't true for what we're looking for. And also, as you can see, B is 1 here. Okay, so that's another little skill that you need to be getting familiar with, is because it's the order at which they're going to be put in. So you've got B is going to be the first value, and then you've got C, which is going to be the next value. So that's how I know which one's going to be which there. So that's the first part. We then take the or C. So we're just going to put in, so treat that completely normal here. And we're just going to go for, where is C1? So C is 1 here. So we put 1 there. C is 1 here, which we put 1 there. C is 1 here, which we put a 1 there. And C is 1 there, which we put a 1 there. We've already had a 1 in there because of before, but that's just to illustrate that. We then draw our boxes around them. So when you're drawing the boxes, and this is a little trick that you need to get familiar with, is that you can do it around 1s, 2s, 4s and 8s. You cannot do it with odd numbers, apart from obviously 1, but you can't be doing it with like 3s, 5s. So it's got to be 1, 2, 4 and 8, and they can overlap in this case. So we draw a box around here, we draw a box around here. And then we're going to be practicing our skills now to make sure that we can actually simplify this into what it is that what we need to go for. So we can have a look on this one here, which that's actually going to be the A and not B. And then we can see that the yellow group here is going to represent C. So in this one, we can't actually simplify. It isn't going to simplify to anything. It's just going to stay as is because the value stays the same. So the only values that stay the same in the green box is going to be A and not B. But this one up here is just going to be to stay as C. So it just the expression is going to stay as is. But it's really good practice for putting those values in there. Now, if we take a different example on this one here, we can have a look at what would this simplify to. So if I just take that out, because that's going to be a little bit confusing because that doesn't actually simplify to that. So let's see what this one represents. So we're looking for where the values do not change. A changes from 0 to 1 for this 4 here. So that isn't going to simplify. B is 0 and 0. So not B there works. C changes from 0 to 1, so it's not that. So what this would simplify to is not B, because B stays as 0 on that one there. So again, have a play around with. What I would do is maybe what you could do is you could put 4 1s in here. So you could put 4 1s in there and be like, what does that simplify to? And it's just about playing around with the different values and thinking about like, what are the different situations that I could get and what would that simplify down to? Now, let's try and do it with this expression here. So here's our OCR up at the top, and this is going to be our Cambridge International version of that here. So what we're going to do is, with the different brackets in there, is we're just going to treat them as they are. So what we're going to do is we're going to start with the first one, which is not A and B and C. So we're going for the not A and B and C. So that one there. So the only situation where that is true, because it's all of them together, is that one there. We then move on to the next one. So not A, B and C for the Cambridge International one is going to go there. This one here, we just move on to the next bracket. Not A and not B and C. A and not B and C, going to go there. Next one is A and B and not C. A and B and not C, going to go to there. A and B and C, so A and B and C, so where they're all 1s is just going to be there. Draw it around those. So we've got essentially 4 different, so we've got, 3 different 2s there. So we've got the green square there, we've got the yellow square there, and then we've got the purple square there. Now, what that is going to simplify down to, if we have a little look on there, is if we take the green one, what is not changing in the green? So we've got A. And then we've also got, so let's have a look at B. So we look at the first value. So A doesn't change, so that's good. So A is going to be part of our first one. And then we've got B is changing from 0 to 1, but C stays as 1. So as we can see here, A and C. So that's going to simplify to A and C. We'll put some brackets around that, and then we put an OR. Let's go for the yellow one. So what is not changing in this one? So B stays as 1. So we can see vertically that B is going to stay the same there. And that would also be the same as if, the 1s were here. You can see that B, not B and not C, if the 1s were over there. So again, play around with different things in there and see what the different values are going to give you. And then also C is going to stay the same. A changes from 0 to 1 though. So we're going to put B and C, B and C. And then what we've got here is then we're going to go for so we've got for the final purple box there. So let's have a look at, so we've got 1 and 1 there. So A stays the same. So that means that we're going to be using A. And we can see that B stays the same. So in there, but C changes, so that's going to be B and C, or A and B, and A and B there. So that's going to simplify down to that expression there, or that expression there. Now, finally, what we have to do is we have to be able to put it into a 4-variable Karnaugh map. Now, with a 4-variable Karnaugh map, so again, looking at how we represent this, so it's the same pattern. So maybe you go for A and B, 0, 0, 0, 1, 1, 1, 1, 0. Just remember to put 3, so it goes 0, 1, 3, 2, 0, 1, 3, 2. I know that doesn't make a lot of sense, but just remember that order because it's how it work. That's going to affect how we simplify everything. So just remember that order of those. And then what we do is we're just going to put the values in there. So the values we've got here is not A and B, or not B and not C and not D. So let's have a look at that. So we take the first bracket, and where that is true is going to be not A and B. So 1, 1, 1, 1, 1. Or, and then let's take the green one, which is going to be not, so it's going to be not B and not C and not D. So where that is true is where we've got zeros for all of them. So it's got to be 0 for B and 0 for C and D. So that's 1, but it's also going to be there because obviously we just ignored the A, so it doesn't really matter what the A is. So those are the two situations where it is. When you're drawing the boxes, you need to remember that these can wrap around the sides as well, which that sometimes can confuse things in there. So it's all about looking at those different situations in there as well. Now, this one we can't simplify it from anything, but I just wanted to show you this as to illustrate the point of how to represent this in a 4 Karnaugh map. And it's utilizing all of those different skills is what's going to allow you to answer those questions, because you're going to get questions where they're going to give you an algebraic expression and they just want you to represent it in a Karnaugh map. So that ticks that box. But then it's also about playing around with how we can actually use those to simplify them, which we did earlier on in the video. So have a play around with it, people. If you need some more questions, just message me to practice. But best of luck. I hope that goes really well. So fixed point is essentially normal binary to denary conversions, but essentially it's just you've got a binary number in, you've got a decimal number in there. So if we go for, just put our numbers in there. So it says 4 bits for a whole number. So 8, 4, 2, 1. Now you can put fractions, or here it's got a decimal, so I'm going to put that. I'm going to put a decimal point there, and then we're going to put 0.5, 0.25. 0.125, and it does say 4 bits even though we're not going to use it, but it would be 0.0625. okay, now you just do your normal binary conversion, so it's going to be 1 for the 8 there, so that's 8, and then the decimal part is going to be 1 0 0 0, like that, and that's how you convert it in there. Okay, if you need to do subtractions, that's absolutely fine, but yeah, that's how you do that, people. This is the other way round. So what it's saying here is, please do make sure that you read the question, because it, as you can see, it does change. So it says 3 bits for the whole number. So I'm just going to put the decimal point in there, 3 bits for the whole number. So we've got 1, 2, and 4 on that one. So that's going to be 5. And then we've got 0. So then we've got 5 bits for the exponent there, which is going to be 0.5, 0.25, and then we've got 0.125 and then 0.625, so 0.0625. Okay, so then so in AQA you have a calculator, so just add them up. For everybody else, what I'd recommend doing is don't be afraid from doing column addition with these, because I just see so many people make mistakes on these ones. So 0, 6, 2, 5, and then just put that in like this. 5, 2, 11, 1. So that's going to be 3. Just one there. Okay. And then we just write in the number after it. So it's going to be 3, 1, 2, 5. Perfect. Okay. So that's fixed point. You just go through. It's just putting the different binary the different decimal numbers above it, which is going to be the main thing which people get wrong. And as long as you pretty much do that, you're going to be absolutely fine on those. Okay. Now, the next one is 2's complement. So 2's complement is how you convert positive numbers into negative. So let's say they want us to convert minus 68, or sorry, 68 into a negative number. First thing that you're going to do is you're just going to convert it into an 8-bit number to start with, just positive. So write all your numbers down. So that's step 1. 8, 4, 2, 1. Okay, that's step 1. Then you just convert it into a normal binary number. So that's going to be 0, 0, 0, 1, 0. So that's 68 as a positive number. And then to a negative number is going to be, we have to 2's complement it. This is my method. There are other ways of doing it, but I personally think this method is way better. You start from the right hand side and you go and find your first 1. Everything at it and before it stays the same. 1, 0, 0. Everything after it is flipped. 1, 1, 1, because they were 0, so now they become 1. And then that becomes a 0, that becomes a 1. So that's how we convert. That there is now negative 68. So just a review on that, what you do, convert it into a positive number to start with. Going from right to left, you find your first number. That is going to be, the first number that is a 1. Everything at it and before it stays the same. Everything after it is flipped. Okay, binary addition. So with this, we're also going to have a little look at binary subtraction after this. So a couple of the rules that, just as a quick reminder, is obviously 0 plus 0 equals 0. Ones, which I see people make quite a lot of different mistakes in there, is so 1 plus 1 is where it gets a little bit weird. In obviously binary, that we can't have 2. So the way that we represent that is we do 0, carry the 1, which I'll show you what that means in a second. 1 plus 1 plus 1. It's 1, carry the 1. Again, I'll show you what that means in a second. Now, I don't think... I have seen it where sometimes when you have to add 3 numbers, but this example isn't actually going to show it. But you could get a situation where you could get 4 1s. And essentially what that has to do is it has to jump over 2 spaces, okay? And I'll show you what that means and how it all fits together. But so they're going to give you this, and they're going to say to you, can you add these 2 together? Okay, so it's always good practice to be able to do this, especially with later on that you have to do the binary floating point addition and subtraction, which if this isn't good, you're going to really struggle with that. So yeah, so with this one anyway, first of all, I'd probably go on the second lot here, because this is where I'm going to put my carries up at the top. So I wouldn't put like the first number there and the second number there. I'd literally just go in the middle and I'd put a number there and a number there, and then I can get all of my carries and everything all sorted. Okay, so that's step 1. And then I'm just gonna just convert the number. So 512 isn't going to go into that, so that's going to go there. 128. So I'll just do a quick bit of calculations there. Put a 6 there, so that's going to go, okay, 6, 4, 0, so we've got 46. It's going to be 1, take that away. That's going to leave us as 14. Okay, so, and then we're just going to go 0, and 14 is 8, 4, 2, 0. Little shortcut and 255. Because I know that for the 9th bit, that's 256, I know that it's 8 1s. So it's like if you got if you had to represent, for example, 63, it would be all of the 1s here as well. So it's just a little shortcut, and it's just because I've been doing it a little while that I realized that. But so yeah, you just gotta go 1 1 1 1 1 1 1 1. Let's have a look at how we do this. So we start from the right hand side and we go 0 plus 1. 0 plus 1 follows the same rules that you know, so that's going to be a 1. Now, when it gets a little bit confusing is when you've got to do 1 plus 1. So we have a little look at our rules up here. If it helps, just write them down next to it, and then you do 1 plus 1 equals 0, carry the 1. 1 plus 1 plus 1 equals 1, carry the 1. That's that rule there. 1 plus 1 plus 1 equals 1, carry the 1. We've got 2 1s there. Confusing thing because people might not have seen it where you've got 3 numbers there, but it's just treat it as this rule up here. So it's going to be 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 1, so again treat that as this rule, so it's going to be 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. Then that's going to be there. And if it did want you to put, you know, all the rest of these bits in there, you just put zeros, but we're not going to do that. Okay, so that's how you do that. Now 3 numbers, so again we're just going to convert these. So we're going to put 19, 0, 0, 0, 1, 0, 0, 1, 1. So 3, 16 is going to give us 19 there. 64 is 0. That was a bit of a weird 0. 0, 64, 0, 0, 0, 0. And then we've got 2 zeros, so that's 66, and then 74 is going to be 0. Then we've got 10 to make up, so that's going to be 0, 0, 8, 0, 1, 0. So as you do more of these, you will get better and better at that. I'm just going to move this up just slightly, just in case you can't see it very well. Okay, right, and then we go through these. So 1 plus 0 plus 0 is 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 0 plus 0 is 1, 1, 1, 0. 1 plus 1 is 0, carry the 1. Then finally got that there, okay? And that's how you do that with 3 numbers. Now, I did say, so let's say for argument's sake, that I had a carry, and I had that, and I had 4 1s there. In this situation, what do we do? So this 4 1s equals 4, okay, and it's not going to go into this column. It's actually going to put a carry on the one over the top of it, and that's quite a difficult one that people struggle with a little bit. So you just got to remember that it is a carry, but it's just going to jump over 1, and it's going to go to that one. So that's probably the best way that I would explain that one, is that it's going to actually jump over the column on that one there. So that's if you get 4 1s. Binary subtraction. Now this is going to use a lot of the same rules that we've actually already done. So binary subtraction essentially works with the principle that if we add a negative number, we get the same result as if we take it away. So you don't have to learn any different rules. It just has a different has one extra step in it where you have to complement it. So you can see this is the reason why I've decided to teach it in this particular order, is because what you're going to do is your binary addition, I'm sure, is excellent, and all you got to do is then you've just got to at some stage complement it, which is what we did before, the second number, and then you're all good. And I've got a bit of a weird example here as well to show you so that you can sort of see how that all fits together. So anyway, we're just going to convert 65 like this, which is going to be the positive number. So that's just going to be 0, 0, 0, 0, 1. And then 43. Now, I'm not going to write this one underneath it because that's where I need to put my negative number. So what I need to do is I'm going to put it as a positive number to start with, which is going to be 0, 1, okay? And then I've got 9 more to make up there for, 11 more. That would have been a bad one. 11 more to make up there. So that's going to be 0, 1, 0, 1, 1. So that's going to be 43 there. Okay. Now, once I've got that, I can complement it. So I use my rule, which is right to left, find your first 1, which is here. Everything at it and before it stays the same. Everything after it is flipped. So 0, 1, 0, 1, 0, 1, 1, right? We've now got that, and we just got to put it underneath this one now. So that's going to be negative 43. 1, 0, 1, 1. Okay, and then we just use the same rules that we did on this page for this one. So then we do 1 plus 1 equals 0, carry the 1. 1, 1, 0, 1, 0, 1, 1, 0, carry the 1, 0, carry the 1. And how this works, people, is this is actually, so as you can see, the number has become smaller if we forget about this one. And what's actually happened is something called an overflow error. So an overflow error is where we actually run out of memory, and this bit gets what's called truncated and just forgotten about. So it's kind of just one of those that somebody worked this rule out, and it actually means that binary addition and subtraction works perfectly in this case. So it will give us the correct number, and as you can see, the number has gotten smaller because there's more ones over here, which is is very interesting. How that all kind of fits together, and it uses that idea of overflow to actually make it work. Just thought I'd show this weird example here and just sort of talk through it. I mean, it's relatively straightforward. Obviously, in maths, the rule is if you take away a negative number, it creates a double negative, which means you have to add it on. So just if they're being a little bit sneaky, just remember that all you're going to do is you're just going to add that 14 on there. So you're just going to do 22 plus 14 because the double negative there means that you're going to get a positive number. But anyway, that's relatively straightforward. Now, going on to floating point. So there's 4 things that I need to show you about how to convert a floating point number into binary. Floating point is essentially has 4 different situations that can occur. A positive mantissa, positive exponent, a positive mantissa, negative exponent, negative mantissa, positive exponent, and negative mantissa, negative exponent. And what that means is floating point is essentially the idea in standard form in maths where you've got like 3.4 times 10 to the 4. Okay, it's just a more succinct way of representing the data. If you had a massive number with this, it's actually going to save you loads of space on a computer because you can have infinitely large numbers on there. And if you can represent really, really big numbers and save a load of space, hardware is only has its limitations. That's going to be great. So that's what the idea of floating point is actually doing, is it's trying to save a space for representing really, really big or really, really small numbers. So the method on this, and I might run out of space on this, but we'll give it a go, is the idea is the exponent, this part tells us where we're going to move the decimal point to, and this one over here is going to tell, and this one is actually the number. Now, for positive mantissas, they will always be 0, 1. Negative mantissas will always be 1, 0. I have seen questions with the exponent where don't necessarily, so 0, it will always be 0, 1 for a positive exponent, but it can actually be 1, 1 as well on some of the exam questions that I've seen. So just look out for that. If there's a 1 at the front of the exponent, you have got to do some 2's complementing. I will show you how that all works. So how does this work then? So the exponent, so step 1 is convert the exponent. So we're just going to put 1, 2, 4. I could put that there, but it's irrelevant. 6. So that tells us that we're actually going to be moving the decimal point 6 places. Okay, the number's got to get bigger. So we're going to go 1, 2, 3, 4, 5, 6. Put a little decimal point there, and then I'm going to redraw my number just so that I can remember where everything is. So 0, 1, 0, 1, 1, 1. Then I just put the numbers over the top of it. So the decimal points here, so that's going to be 1, 2, 4, 8, 16, 32. And that's going to be 0.5. So 32 plus 16 is 48. 48 plus the 8 is 56. And then plus the 2 is 58. And then we've got 0.5 there. So let's just add that on there. So that number there is going to be 56.5. 58.5. I do apologize. So yeah, 58.5 there. Okay, so that's how you do floating point mantissa. Just going through those steps again. Exponent tells you how many times you're going to move the decimal point. The mantissa tells you the number on this. So the actual what the number is. So you work out the exponent, you move it, and then what you do is then you just convert the number in normal fixed point binary, which we did before. So as you can see why I've taught it in this particular order, and that gave us 58.6 in there. So that gives us all of that. Now I'm actually just going to take this out because I need more space for this one. So floating point, so positive mantis and negative exponent. You can see here I've got a negative exponent because I've got a 1 at the front. So step 1 that I need to do is I actually need to 2's complement this. So find my first one, everything at it, and before it stays the same, everything after it is flipped. 0, 0, 0. That then gives me a negative 1. Okay, with the negative 1, what that's going to tell me is that I have actually got to make this number smaller. Okay, so before I can move the decimal point, I have to move it to the left, but to do that I need to actually put an extra 0 in there. what I'm going to do is I'm going to move that over to here. And I'm going to do 0.01. Yeah, so you put in the number of zeros for the exponent. So if I had -3, I would put 3 zeros there, and so on. -4, I put 4 zeros, and then I just redraw my number. So 0.0111, like that. I could put in the rest of the zeros, but they're not going to have any bearing over my actual answer. And then just write the numbers in there. So that's going to be 0.5. I'm going to show you how to do it with a fraction, actually, because I personally find it easier with the fractions. But, you know, if you find the decimals easier, you know, use the decimals. There's no problem in doing that. It's just personal preference, and it's still correct either way. So put the fractions in like that. So half, quarter, eighth, 16th. So to add that, in here, you know, so what we're going to do is we're going to times this by 2, because to add fractions together, the denominators both have to be the same. So then that gives me 2 over 8 plus 1 over 8, which that's going to give me 3 over 8. Okay, and then final thing that we've got to do is we're going to times that by 2, which that's then going to give us, for the 16 on the end there, so that's going to give us 6 over 16. Then we're going to add the 1 over 16, which then that gives us 7 over 16. Okay, so that's our answer there. So personally for me, I find it easier to use fractions, but that's it's personal preference. If you prefer using decimals, use the decimals, that's fine. So okay, so in those ones there, what we're going to do now is we're going to go for the negative mantissa, positive exponent. So I'll move this one up a little bit, and what we do is we go for the. So what we do is we can see that we've got a negative mantissa, which is where this one here is. It's got a 1 0 there. So what we do is it doesn't really matter which order that you do this in, but 2's complement the exponent, which is 4. That tells us that we have to move it 4 places to the right. The number is going to get larger, and then what we then need to do is 2's complement this before we start moving the exponent. So that's the decimal point, which is where I see a lot of people go wrong on this one. So that's going to be 1 0 0 0. So right to left, find your first one, everything at it and before it stays the same, everything after it's flipped, 1 1 1 0. And then what we're going to do is we're going to move to the right. So we're going to go 1 2 3 4. Then so the decimal point is going to go here, which then that's going to go 0 1 1 1. And then we have got a 1 right at the end there, so we just do need to take into account about that. So it's like that. Okay. So that is going to be 1 2 4 8. So that's going to be 14. And again, you can just put the fraction here. So that's going to be half, quarter, and an eighth. So 14 and an eighth. Now, mistake where everybody always makes on this one, they forget to put the minus in there. If you forget to put the minus, you do lose a mark on this one. So be super, super careful, people. If it's a negative mantissa, it's a negative number. That's what it's telling you. So just be careful on that one there. Okay. Final one is negative negative. So negative negative is where you've got a negative mantissa and a negative exponent. So what this one is where you have to 2's complement both of them. So what we're going to do is we're going to go to here, 0 1, everything at it and before it stays the same, everything after it is flipped. So so here is going to be 0 and 0, and then that's going to give us -2. Now what we would do before we added so we would 2's complement this first, and then we're going to add the zeros in. So I go right to left, so it goes to this one, everything at it and before it stays the same, 0 0 1, and then everything after it's flipped, 1 1 0, decimal point in there. Now this is telling us that this is going to get so we need to move it 2 places. So we're going to go 0 0, and then we're going to go 1 2, And then that redraw our number, so it's going to be 0, 0, and then we're going to get a very, very small number on this one. So that is going to be a, so just double check I did that correctly, because that's 0. Yeah, no, it is. So that's going to be 1, 2. Yep. So here, now what we have to do, I'm going to use my fraction, so half, quarter, eighth, 16th, 32. Okay, so they're adding so times that by 2, that's going to give me 2 for 16 plus 1 over 16, which that then gives me 3 over 16. 3 over 16. And then I need to times that by 2, so then that's going to give me 6 over 32, so that I can add it to the 1 over 32, which is going to give me that. Now, mistake which everyone makes, forgets to put the minus in. So negative mantissa, it's just a very, very small negative number, which is minus 7 over 32. Couple of little, that's in a bit of a weird format. Just a couple of little sort of 1, 2 markers that they seem to like to put in. That's a bit easier to read. There you go. That they like to ask. So for this question up here, it's what happens when you increase the precision of a number, and what happens when you increase the exponent of a number. So if you increase the mantissa, the number of bits, or decrease them, vice versa, increase the exponent, decrease the exponent, what happens to the number? The mantissa is where so what happens is you increase the precision. It just means that the number can be more precise, and like you can be more specific with the number that you're trying to represent. So that the key word that they're looking for there is that the precision is increased, and the inverse is also true. If you decrease it, then the precision decreases. The exponent is there's a greater number of numbers that you can actually represent if you increase it, and then the inverse is also true. With this, overflow can also happen, is the number is too large to be represented with the number of bits that you have available. Underflow is too small to be represented with the number of bits available. Is probably, I'm actually going to change that with number of bits available. So I'm just going to slightly change that one there for you, because I personally think that's a bit of a better sentence there. There you go. Number of bits. Number of bits available. So there you go. There you go. Sorted. Last bit, people. Last bit. Oh, actually, I think we've still got a little bit more, actually. So, well, we'll keep going. Okay, so normalization. Normalization is the idea of essentially if we have a number here is 0.34, okay, times 10 to the 3. What happens here is this number isn't actually normalized until it becomes this. So because I've moved the decimal point to here, I actually need to make this one smaller, that's going to be times 10 to the 2, okay? And it's the same principle as in normalization. Positive numbers have to be 0.1, and this one over here needs to be 1.0 because there's 1s at the front. If it's positive, it needs to be that. If it's negative, it needs to be this. So in this case, what we're going to do is we need to see how many times we need to move the decimal point. So remember, positive needs to be 0, 1. So I'm going to go find my first 0, 1, 1, 2. So then that's going to be 0, decimal point, 1, 0, 1, 1, 0. Add in the zeros that you need there. Now I've moved it 2 places, so I need to subtract 2 away from my exponent because I've made the mantissa bigger. So I need to make I need to counteract that with the exponent and make that smaller. So that's 3. So I subtract 2 from that. So then that is going to be 0, 0, 1. So move the decimal point. Then once you've moved it that number of times, what you then do is then you subtract it from the number, the exponent. For this one, we have to look for 1, 0. So the first time we've got 1, 0, which is there. So again, same principle. 1, 2, 3. Okay, that's great. And then we're going to go 1, 1, 0, 0, 0, 0. So just add in zeros for the rest of it. And then we had to move that 1, 2, 3. So we moved that 3 times. So then that's going to be there. Take away 3. So it's going to be 0. That's 6. So now this will equals 3. So again, just make sure, because it's a negative number, it needs to be 1, 0. And then that's going to become 0, 0, 1, 1. Tying this all together, we have to be able to convert between denary numbers and floating point as well, so go in the other direction. So first things first, what you need to do is you just need to convert it into a normal 8-bit number. Now we have got a decimal number in here, so I'm going to put 64 here, and then I'm going to do 32, 16, 8, 4, 2, 1, and then 0.5. Okay, and then I just convert 45 like so. So I'm going to go 0, 1. I've got 13 to make up there, so that's going to be 0, 1, and then it's going to be 1, 0, 1. So that's 45, and then the 0.5 is going to just be there. Decimal point is here. So that's the first stage, is just convert it into fixed point binary. The last stage is where we are actually going to move it. We have to essentially, normalize it like we were doing on the other ones, but this tells us what the exponent is going to be. So I need to move it so that it's on where it's 0, 1, and it's got to be the furthest 0, 1 on the left hand side. So we're going to go 1, 2, 3, 4, 5, 6. So we move that 6 times. Just put a little decimal point in there to help you remember. 1, 0, 1, 1, 6 times, and then our exponent is going to be 0, 1, 1, 0, because 1, 2, 4. Yeah, so on there. So 8 bits, 1, 2, 3, 4, 5, 6, 7, 8 for our mantissa, and 4 bits for an exponent. 0. So 1, 2, 3, 4. Okay, and that's the answer there. Okay, so that's how we do that. Converting a negative number into floating point. So we just have to go through a couple of stages on this one. It's just an extra step. Once you've converted it into fixed point, you just need to convert it into, you just need to 2's complement it, and then just make sure that the decimal point goes between the 1 and the 0 there. So on this one here, we're going to go for, we'll go for 64, 64, 32, 16, 8, 4, 2, 1, and then we're going to do 0.5. Okay, so then we're just going to put our numbers in like so. So we're going to go for 14, which is going to be 0, 0, 0, 1, 1, 1, 0, and then we'll put in a 1 there. Okay, so with this one here, what I'm actually going to suggest is, instead of us having a load of leading, actually no, that is correct. So yeah, we'll go with that. And then what we need to do from this point is we're going to actually 2's complement it, because it's a negative number. So what I'm going to do is I'm going to go right to left, find my first 1 and everything at it before it stays the same. Everything after it is flipped. So 1, 0, 0, 0, 1, 1, 1. Once we've got that, then the big thing to remember on converting a negative number is that it needs to go in between the 1 and the 0. So on the left hand side. So it's going to be this position here. So I'm going to move it. So I'm going to go 1, 2, 3, 4. I can actually forget about these ones, so I'm going to put 1, 0. So I'm just going to go from here, 0, 0, 1, 1. And if it wants it as an 8-bit number, I need to so that's then going to be 2 more bits there. And then I moved it 1, 2, 3, 4. So the exponent needs to be 4. So that's going to be like that. So that's 4 because 1, 2, 4. And then this one up here is then going to be a negative. That's then converted into a negative number and ready to be converted back at some point. So on this one, brilliant. Okay, so the last little part of this is being able to add 2 binary numbers, floating point binary numbers together. I did write down some little instructions as well, just to help you out as well. There's kind of 5 stages, 6 on when we've got to subtract them, because you've got to add them and to be able to subtract them. Now, with the last little part on here, if you imagine with like 3.4 times 10 to the 3, and then I had to add like 2.7 times 10 to the 5, the way that the method in which I would do this is I would convert it first and then add them and then convert them back into standard form. I can't just like start adding them because it's not going to work. So yeah, it's the same principle in this. So what we do is we go for, so yeah, 2's complement them to start with, and then you're just going to use not 2's complement them, sorry. You convert them using the floating point method, so you move the decimal point, then you can just add them. You don't actually even need to convert them into denary, and then you add them together, and then you can convert them, normalize them again, and then it's all good. I'll show you what I mean. So this one here is, so that's going to be 2. So what I'm going to do is I'm going to move this 2 places to the right, so 1, 2. Now, very, very important that we have to match them up so that that all of the values are in the same place, and I'll show you what I mean by that. So what we're going to do is we're going to go 1, 1, 0, 0, 1. I could put in the other numbers, and I may have to pad it out with if the numbers are are a little bit different from each other. That's absolutely fine, and I'll show you how to do that in a second. This one here is 4, so I need to move this 4 places, so that's going to be 1, 2, 3, 4. Decimal point is going to go there. Then in this case I have to, so I put that under there like that, and then can you see on this one here I'd go for like 0, like that 0 goes under this one, even though that they're not in the same place. It's because the decimal point is there and the decimal point is there, so I have to match it up. 1, 1. Put some zeros just to pad it out up at the top, and then also we need to make sure that we get the 1s here as well, people. So, and then put a 0 there just to pad that one out. Add them together. I'm just going to move this up slightly just so, in case some people can't see very well, so I'm going to move that up. So then what I'm going to do is I'm just going to add it up. So 1, 1, 1, 1, 1, 1, 1. Now it is positive, so I'm going to add in another 0 there. Okay, so the principle of this now is, so I've added them up, everything's lovely, and all I'm going to do now is I'm just going to move the decimal point now. So that's going to go 1, 2, 3, 4. Remember that you've moved it 4 times. And then the exponent now is going to be 4. Just make sure I did the correct number of 1s there. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And that's how you do it there. So I'll just go through the steps because there are a lot of steps with this one. You exponent, so move it, move them, then write them in their respective position. So once you've converted the exponent and you've done that, then you just add them all up, and you then make sure that you normalize it so it's 0, 1 or 1, 0 if it becomes a negative number. And yes, so that's going to that gives us that. And then once you've moved it, you just count the number of times that you moved it. It was 4 times, and that gives us 0, 1, 0, 0. Okay, final one to do, final one. So with this one here, what we need to do is we just need to go for subtracting a negative number. Sorry, not subtracting a negative number, just subtracting a number. And with this one, we're actually going to get a negative number as an answer because I believe the number underneath is larger. And you kind of just get better at realizing that this is happening. And a little check that you can do if you've got time in the exam, if you're a person that kind of goes right up to the end in exams, I'd maybe just suggest if you go right up into the exams, just go through the steps, you'll be fine. But if you have got time to check, you can just convert them into their equivalents, and you will actually see that in this one, this number is larger than this one. And the exponent also can sometimes give it away a little bit, because that's actually going to be, it's 3 and that's 2, so it's the likelihood is that this one's actually going to be larger. So the answer should be negative. Anyway, so let's have a look at how we do this. So step one of what we're going to do is we are going to just do our normal thing, which is convert these. So that's 2 and 3. Okay, now we have to add in an extra step. So first, this one here, we're not doing anything different with this one. So the decimal point is going to go there, and I draw my number. 0, 0, 1, like this. Perfect. So that gives us that. Oh, that gives us that. Now, once we've got that in there, all I have to do now is I'll just put an extra 0 there as well. With this one here, I actually need to 2's complement this one, because we're going to use that principle I was talking to you about when we were doing binary subtraction, that if we change it to, if we add a negative number, it has the same effect as just taking it away. So we don't have to learn any different rules. We can just go with that. And this one here is I need to move this. So what I need to do is I need to actually 2's complement this one, because we're going to change it to a negative and then add it on. So 0, 0, everything at it and before it stays the same. Everything after it's flipped. 0, 1, 0, 1. Okay, decimal point is there. We know that this is 3, so then we move the decimal point. So 1, 2, 3. Okay, remember that we've put it there. Okay, so that the 1 is the other side of the decimal point. We put that there, and then that's going to be 0, 1, 0, and I'm going to put a little 1 there. Okay, now put in some zeros there, people. That's going to essentially work in that particular way. Then we just add them up. So we're going to go 1, 0, 1, 1, 0, 1, 1, and 1 on that one there. So the decimal point is going to go here. In this particular case, what I'm actually going to do is, remember me saying to you that this number is larger. So we're actually going to get a negative number there. So a mistake that some people might make is they might put a 0 there and go for that and be like, oh, it's positive. We're actually going to go here. Okay, so it feels a little bit weird because we're like, there's a 1 there. Like, are we not getting rid of something? It's a negative number. That's actually what we want to happen. So in this case, we're going to go for the 1 and the 0. So what I'm going to do is I'm going to go 1, 2. Forget about this 1 up here, and then I redraw my number depending on where how many bits it wants me to do. So I moved that 2 places. So 1, 2, 3, 4, 5, 6. So I'll put in a couple of zeros, just pretend it was 8 bits that it was looking for. The decimal point is here. I moved it 2 places, and then the exponent is going to be 2. Okay, people. I think that was the longest video I've ever done. I hope it was useful, and I really, really wish you the best in your exams, because they're very hard, and I just hope that it helps you out. Take care, people. Thank you very much. Okay, von Neumann architecture. The A-level definition for this is a CPU that has 1 bus and 1 memory location for data and instruction. That's the first point. So it's just that they're stored in one place. It also has a control unit, and an ALU is another point. It fetches, decodes, and executes instructions from RAM. So there's probably a little bit more than what you need there, people, but those are the points that I would use. Harvard architecture is where you've got a processor that has separate storage spaces and buses for data and instruction. So data uses its own individual bus. Instructions has its own individual bus, and they all have their own memory locations. Because of the sort of application points now, so Harvard architecture is normally used for quite high processing embedded systems. The reason for this is it's actually quite a complicated program, a complicated system to work. So they need to do it with simpler tasks, but it does allow for essentially you don't suffer from bottlenecks that you would get in von Neumann because you have got the 2 separate buses. So those are some application points that you can use there. Purposes of individual components of the CPU. ALU performs mathematical operations. Everyone remembers that because of arithmetic, but then they also forget to put in the logic gates. That's how you get the second mark. Control unit, does the decoding and executing part of the FDE cycle, sends control signals to other parts of the CPU. Cache stores frequently used instructions so that you don't have to go to RAM to fetch it. Different buses within the CPU. I have no idea why they like to know this when you're describing them. So the three of them, you'd get a mark for just stating them because they'll be like state and describe a bus. I've put them all there for you, so you can make a flashcard for each of those. Control bus, 1 mark. I don't know why they like to know about whether it's bidirectional or unidirectional. So data and control buses are bidirectional. Address bus is unidirectional. Control bus essentially sends out control signals to the input and output devices and main memory. Also receives data from them. The idea of that being bidirectional. Data bus, just remember that it does data and instructions. Address buses sends the addresses and retrieves them from the processor. Okay. The specific registers. Now, if they would just get you to state and describe them, the three you need to know 1, 2, 3, 5. Sorry, I don't know why I said 3 there, but yeah, you need to know 5. The point with these is if you can just remember one sentence about these. Okay, so it's holds the address of the next instruction to be executed, program counter. Holds the address of the current instruction being executed, memory address register. Holds the data that is currently in use by the CPU. Holds the result of any calculation done by the ALU. And then the current instruction register holds the instruction that currently being executed. Okay. I know that sounds really, really confusing, and at A level you are starting to get a bit more familiar with this stuff because I'm hoping that you've done some of the assembly code stuff. If you haven't done any assembly code stuff for whatever reason at school, I am going to show you how that all fits together. But what I've tried to do is use my knowledge of looking at the mark schemes to give you as little as possible to remember, and you still be able to grab a mark on this. At A level, they would probably be a second mark attached to this, and I'm going to show you how to get the second mark. But the way I've tried to make this more simple is, can you see for program counter it says holds the address of the next instruction to be executed, and then memory addresses holds the address of the current instruction to be executed. The definition is very similar. The only difference is one is current and the other is next. So one definition, you change one word and you still get the marks for it. Memory data register holds the data currently in use. So only word there that's changed is data. So again, 3 definitions, but you only use one. Current instruction register holds the current instruction being executed. So again, you just change instruction. I've put in the other little extra points as well in case they give you a 2-mark question in there as well. So program counter increments after the data is passed to the MAR. Second mark there. Memory address register receives address from program counter. Second mark. The accumulator is where data decisions are made from. Where branching decisions are made from. When we look at assembly language, well, this will make a little bit more sense, but you use things like BRZ, BRA, BRP. That is essentially how you create decisions happening there and loops and in assembly language. The accumulator is where that decision is made, so that's kind of a little extra point. The other one is input and output device. Input and outputs come from the accumulator. The current instruction register is it splits into operand and opcode. If they wanted a second mark for the memory data register, I would say that when it fetches the data from the CPU fetches the data from main memory and brings it back to the CPU and stores it in the MDR. I have no idea why this was such a big thing, but I remember when I was marking one of the papers, and you'll notice that I changed the way that I said that, which was all to do with these are just memory stores. We weren't allowing marks 1 year. This may have changed now, but we weren't allowing marks 1 year if there was an inference that the registers were like doing any of the passing. So can you see I haven't said the program counter passes the data to the MAR. All I'm saying there is that the data generically is passed to the MAR, and you're probably thinking that this sounds absolutely mental. Like, why am I going into so much detail on this? They are just memory stores, and the thought process behind this was the CPU is doing the passing of the data. These are just storing the data. And it sounds ridiculous now that I'm saying this sort of out loud, but we weren't allowing marks on one and then the other. I didn't make the decision, but it's just I do remember that. So just making sure that you're not saying like the program counter passes the data to the MAR, or the MDR gets the data from the RAM. It's the CPU which does that. I know that's a little sort of, if that sounded a little bit confusing, just get these definitions down. That's the most important thing. More of an A-level thing as well is the idea of the FDE cycle. So you need to know what the registers are doing at each individual stage of the FDE cycle. So it could be a fill in the blank. It could literally just be what are they doing what are the registers doing at the fetch stage of the FDE cycle. So I've tried to list it and number it for you. Address is copied from the PC to the MAR. Again, no inference that the program counter is doing it, like that. The instruction held in the address is copied to the MDR. This will help you with some of the points on the previous one as well. Simultaneously, probably don't need the word simultaneously, make it easier for yourself, give yourself less. The contents of the program counter are incremented, less to remember, more likely to remember it. The contents of the MDR are copied to the current instruction register. So that's the fetch stage. Decode stage. Decode stage is the instruction held in the CIR is decoded. It's split into operand and opcode to determine the type of instruction. Additional data, if required, is fetched from memory. We'll get rid of the if required. I'm always trying to give you as little as possible to remember, and passed to the accumulator. Execute. Control unit carries out the instruction, sending it to the ALU. Results stored in the accumulator. ACC is just an acronym, and you can use the acronyms to describe them as well. So fetch, decode, execute. Know that off by heart. State and describe a method in which the CPU performance can be improved. I've put 2 on here, and then on the next slide I've put the other 2. So clock speed is one of the first ones. You can increase the CPU speed by increasing the clock speed. The clock speed is, so if you have a 3 gigahertz processor, that means about 3 billion fetch, decode, execute cycles happen per second. So the higher that is, the quicker the computer is. A computer core, so number of cores, if it has more cores, generally this is going to be faster. This is because it can work on different things simultaneously. We're going to have a look at pipelining in a second and what that means. And essentially what this is if you have multiple cores, you can do something called parallel processing, which just means you can do things all at the same time. Cache is another one. So it's the same question. I'm just putting all of the points on there. Cache is essentially a little memory store in just within the CPU, and it just means that the larger that is, you don't have to go to RAM to fetch anything. So it stores frequently used instructions. So the less you have to go to RAM, it's going to shorten that space. Then it's going to simplify the whole process. Pipelining is one that you won't have heard at GCSE, but pipelining is a one which is every core is doing something, a different part of the fetch, decode, execute cycle. So it's this idea that one core is fetching, while the other core is decoding, and the other is executing. So, and you need to say it in that way. So one core is fetching while the other is decoding and the other is executing. And this allows for parallel processing. And all 3 of that, it's normally a 3-mark question. You get 3 marks there. Very quickly, what they might get you to do is they might just get you to calculate which is going to be the faster one and why. So you've got a gigahertz, this one over here, 1 gigahertz, and you've got 4 cores, 1.4 gigahertz, 2 cores, which is faster of why. Generally, ignore the cache. If they are the same, that could be like the tie break factor, if you get what I'm saying. So I'll explain that. 1 gigahertz is 1 gigahertz times the number of cores. So total clock speed is clock speed times the number of cores gives you total clock speed, which is 4 gigahertz. The other one is 1.4 times 2 equals 2.8 gigahertz. Comp 1 is going to be faster for the flight simulator in this case because it has a higher total clock speed. If they happen to be the same, and then you had the cache size, and that was the only deciding factor, then you might make a case and say like, well, they've got the same total clock speed, but the cache size is the same. The cache size is different, and this one is larger. That might be the sort of tie break between the 2 of them. Embedded systems, the definition for this, if they just ask you like what an embedded system is, within a computer system within a larger system with one purpose: fridge, microwave. An embedded system, they may also say like what is an embedded system in a particular situation. I've used a car there, car parking system, GPS, automatic windows. The alternative to that is a general purpose computer, and a general purpose computer is what you're using right now, I would suspect, which can perform multiple tasks on multiple purposes, e.g. desktop computer, all that stuff. Linking that back to von Neumann and Harvard architectures, generally von Neumann is general purpose computers. Embedded systems are Harvard architecture. Okay, so we've got that one. Okay, right. So now going on to primary storage, and I think the definition is actually changed on this. So I'm just going to leave it to that. I'm going to take those two out on that one. So give an example of primary storage. It's a piece of memory that is directly connected to the CPU, which is RAM and ROM. For a while, I remember that they did use, I think it was in like maybe 2018. Anyway, you don't want a history lesson on it. Essentially, they use cache and registers, but I think they've changed that now. So I'm going to leave it out because I don't want to take any risks. We're just going to say RAM and ROM because we definitely know that. Sometimes the definitions change with what people are given marks for and stuff like that. So let's go with that and not take any chances. Secondary storage is the idea of non-volatile permanent storage for files and applications when not in use by the computer. The concept, if you just remember the definition, great, that's the kind of first step. But the understanding of this is when I want to use something, I load it from secondary storage, which is when it's almost like dormant, and then I load it into RAM. Then what happens is I'm working on it. So right now, like my PowerPoint is working on it, and essentially what with that, I'm getting the data and instructions and everything from there, and it's that idea between the two of them. ROM has some really, really important programs and instructions on there, which we'll talk about more in a second. But yes, generally it's the idea that you go from secondary storage when not in use. RAM, we load it into RAM and we start doing stuff on it, and then when we don't want to use it, it goes back into secondary storage. They do sometimes get you to compare the RAM and ROM. I was doing some questions with a student the other day, and did have this. RAM stores instructions and data that are currently in use by the by the computer. It also stores the operating system, which is in use by the computer. ROM stores the BIOS and bootloader. The BIOS and bootloader are some of the most important programs on the whole computer. We do not want these to be changed. We do not want these to be edited, because when you turn the computer on, the bootloader is the program which essentially loads the operating system into RAM, essentially turning the computer on. So this is one of the most important programs on the whole computer, which is why ROM is read-only. RAM is read and write, which essentially just means that you can change stuff on it, which makes sense because it's the stuff that we're using in this particular moment in time. ROM is just read only. We can just read it because when we turn the computer on, that's what we want to do. What does it store? So we've kind of talked about that already on those ones. The other sort of, if they ask you to compare them, RAM is what's called volatile. When you turn the computer off, it doesn't remember anything on it. ROM is non-volatile, which is when you turn the computer off, you still want to be able to have all of the things on there, because if it forgets the BIOS and bootloader, we could never turn the computer back on again. State the purpose of ROM, kind of already done that there, but I guess that's just not putting it on a table. So I'm going to skip that. Talked about volatile and non-volatile already on the previous one, so I'm going to skip that as well. If you want to make flashcards on those, I'll just leave it up there. Leave it on there. There you go. Okay. Virtual memory. Virtual memory is it's essentially where we run out of RAM. The computer can either crash, or what can happen is it can actually use virtual memory. Virtual memory is where we use part of our hard drive and we use it as RAM because we've run out of space. Now the idea, which I guess is probably a little bit more of a you might want to add on there is linking this to the operating systems unit, which I don't think I'm going to have time to put out a lesson before paper 1, so I'll tell you about it now. One of the jobs that the operating system does, so let's say that you get a question which is operating systems, and it will ask you to describe some of the jobs that the OS does. User interface, definition to use on that one is hides the complexity of the hardware from the user. And then you can, if you need to give an example, graphical user interface, command line interface. But the other one that you can talk about is memory management, and you can use and say, like, it does memory management, and it does this thing called paging, which is where it's essentially puts data into chunks, and what it does is it loads these pages into from RAM into the CPU, and these pages have to be what's called contiguous. Tying this together with virtual memory, one of the jobs of the operating system is actually to, when we run out of RAM, is to use virtual memory. And if you talk about that in there, so if you get a question where it's like, name a job of the OS, and you can go memory management, you can say, oh, it creates pages, and the other one is segmentation. And it also does the virtual memory, which is when the hard drive, when the RAM runs out of space, that it uses part of the hard drive uses part of the hard drive and as RAM. And what it does is it loads things from the hard drive into RAM so that it can be used by the CPU. Now, the advantages of this is it's virtual memory stops the computer from crashing. Big advantage. The bad thing is, though, is it's very slow, and it creates this thing called disk thrashing, which is where the whole process and everything just slows down, and it's it's just a lot slower. So that's the kind of main thing. And if you use the key term disk thrashing as well, that would give you a mark just for that as well. So that's virtual memory. Okay, secondary storage. We gave a definition for secondary storage already, but the three main types is that you've got solid state, magnetic, and optical. Now, with these, so this one is optical, and you also got to know how to describe how it works. Don't know why we still do about CDs and DVDs, because they kind of, no one really uses them that much anymore. But anyway, examples of CDs and DVDs. If it asks you about a scenario and you need to give some kind of advantages and disadvantages about this, quick advantage is CDs are portable, but the main problem is they get scratched really easily and they're easy to damage. So optical, first mark, disc spins and laser is shot at the disc. Okay, so disc spin 1 mark, laser is shot at the disc is 2nd mark. So yeah, you get those. There are these things called pits and lands, which go out a spiral from the middle. So 3rd mark. The laser reflection is measured when it passed over the pits and lands. 4th mark. It then determines whether it is a 1 or a 0 based on whether it goes over the pit or the land. So 5 marks there. If it's 4 marks, then you don't need to put as much. Hard disk drive. I always try and make it as simple as possible for you to remember. HDD has a disk which spins, so same as the CD. So HDD is an example of magnetic storage, by the way. Disk is split up into tracks and sectors. A read and write head passes over the different areas and reads whether the data is a 0 or 1. I would actually also add on there that how it does that is it has magnetized particles, and whether these particles are magnetized or not magnetized is the thing that determines whether it is a 1 or a 0. If they give you a situation where they're asking you for your recommendation of whether you would use this, I have seen this one situation where generally you use solid state in every situation, which we're going to talk about. But say if there was like a budget constraint and there was a company that maybe didn't have as much money, and it was maybe trying to do something for like backups in the evening, where speed, like, even though HDDs, like, they have actually quite quick write speeds, not as fast as solid state, but it's not absolutely essential that you have to do everything as fast as possible, and it's cheaper than solid state. You could use magnetic storage as a backup. So that would just be the one situation which I just thought I'd draw your attention to on that one. I think I skipped one. Yeah, okay, so solid state. Solid state works by having an electrical charge that is either trapped or not trapped by NAND gates. If it's trapped, it's a 1. If it's not trapped, it's a 0. And then this is red. So you'd always, with every single one, just make sure that you know how to describe whether it's a 1 or a 0. Examples of this is SD, USB, solid state. Advantages: it's portable, has the quickest read and write speeds. The only real disadvantage is that it is slightly more expensive than the others. Just in case you get a question about cloud storage. Now, weirdly, they called cloud storage, I think this was on OCR, maybe on AQA as well. They called cloud storage virtual storage for a while. I don't know whether they've changed that now. And I think they may have changed that because of the confusion with virtual memory and virtual storage. Like, they sound kind of the same thing. So just be careful of that one, because if they kind of like in the question, they seem like they're talking about virtual storage, and it seems like they're referring to clouds, or like, you know, people working in other places. They're talking about cloud storage, so just careful on that one. Cloud storage is where the storage is not held on the actual device but in a remote server in another location. It requires an internet connection. The advantages of this, just quick ones: can access files from any device as long as you have internet, easier to collaborate with other people. Negatives, though, is has to have an internet connection to access it, and you are trusting a third party with the security of your files. Whilst the security, I'm sure, is very, very good, we are trusting people that they're going to be good. Couple of little input and output devices. I was having a quick look at the ones which I thought maybe were a little bit not so obvious. Barcode readers. The way it works is it reads the thickness of the line. So you've got guard bars, which are just almost like, I guess, almost like the quotation marks around when you're writing in a print statement in Python. It's like saying, like, this is the area you're going to look at. The light shines on the barcode, and that then can measure the thickness of it, and then that turns it into a number, which will be an equivalent to, for example, in this case, a banana, and then other little extra bit that you have to put in there. That then is linked to a database which will subtract 1 from there and say that you have 1 less quantity in stock. So shine a light on there. So you shine the light, that measures the thickness of the lines, that then links to a database. The database subtracts 1 from there. Sometimes they sort of ask, like, how does it automatically like reorder stuff? So you would say when it gets to a certain quantity in the database of numbers in stock, it automatically reorders that from there. So I just thought about barcodes there. Digital cameras break up what it sees into a grid of pixels. The shutter opens to let light in onto the sensor at the back of the lens. The intensity of the color of the light is measured by the tiny sensors of each of the different pixels. Laser printers, they use something called toner. Don't use liquid ink. It uses an electrostatic charge to produce text and images on paper. Generally, laser printers, they use that over inkjet printers for large numbers. So that's why schools, organizations use laser printers, because if you need to do 100 copies of something, it does it really, really quickly, because it does it the whole document. For 1 or 2 copies, it's actually quicker to use an inkjet printer, which is just probably the one that, if you have a printer at home, it's got that one there. Okay, so that is going to be everything for AQA. OCR and Cambridge International, I just need to go through a bit of RISC and CISC. So CISC processor. Now, with this one, essentially what we are going to do with this one is there's 2 different sorts of processor styles, and they are to do with the amount of instructions that they hold. So CISC processor has a really large instruction set that is used to accomplish tasks in as few lines of assembly code as possible. They're a bit simpler to use. I remember there was a question where they asked you, a company was thinking about upgrading its computer systems, and I just thought it'd be good to have a couple of advantages and disadvantages about this. generally think of CISC as like what you're familiar with using. And in the answer, it was all to do with that these people were familiar with using CISC. So the big advantage is that as a company, you don't have to spend time training people on how to use risk, which I'll talk about in a second. You don't, there's not going to be a time where people are making mistakes. People are just familiar with using it. Disadvantages, though, is that it does have a higher power consumption than risk. And it doesn't allow for pipelining, which we talked about is really can speed things up. So risk, very small. It's got simple instructions, so you haven't got an instruction set which is very large. One clock cycle can accomplish all the required operations in so it's just one clock cycle per instruction, so it's very fast. Advantages, it's very fast when it's using pipelining, low power consumption. People aren't super familiar with this though, so they aren't. This isn't something that they know, so that you would have to spend time. People are going to make mistakes. That's going to cost the business money. Anyway, so what I'm going to try and do is for tomorrow, I'm going to try and get a little thing about assembly language for you all. But I hope that was useful, and I wish you all the best for exams that you've got coming up. But what is a database to start off with? An organized collection of data into fields and records. A flat file database is a database that only has one table. An entity is a category of object, person, event, or thing, or of interest, which the data needs to be recorded. You would normally see a well-made database will have a table per entity. Now, in badly made databases, you actually have the entities all mixed up together, which we're going to talk about some of the problems with a flat file database where all of the entities are mixed up with each other. A relational database is where you've got more than one table connected through relationships. You would also use foreign keys and primary keys to connect those. A primary key is a unique identifier of a record in a database. Foreign key, a primary key from another table used to create a relationship between the two tables. And a secondary key. So a secondary key is very similar to a primary key. It uniquely identifies a record but isn't the primary key, and can be used when narrowing down a search or indexing of the data. Entity descriptions, sometimes they ask you to do an entity description. Now the table name, the table name is going to be displayed on the left hand side, so like customer, product, and subscription. The entity descriptors, or the field names, so the column names, they would be displayed here. So you've got customer ID, title, first name, surname, and email. And then the other thing that you've got is you need to have the primary keys underlined. So the primary keys are what uniquely identify each of the records in there. Now, when we start talking about normalization, composite primary keys are where we join two attributes together to create a unique identifier for this. So for example, we could join together order number and order line to create what's called a composite primary key. This will become more important when we start talking about normalization and how we go from an unnormalized database into third normal form. But generally, that's what a composite primary key is where we take two identifiers and join them together to create a unique identifier. One of the questions that you could get is where it will get you to do what's called an ERD diagram, which is an entity relationship diagram. And there's three different relationships that you can get. You can get a one-to-one, a one-to-many, and a many-to-many. Generally, you will always be trying to go for either a one-to-many, or in a perfect circumstance, or you'll be going for a one-to-one. A many-to-many is generally seen as is not good, and we will be talking about why that is in a second. But things that you can do when you're trying to draw your entity relationship diagrams, a couple of little tips, is if they're giving you some databases and they've given you the different tables on there, a one-to-one would be a situation where, so the example I've given here is a car and the employees. So one employee has one car, so that it's a one-to-one, one employee to one car. A one-to-many might be a mother to children. So the mother has multiple children, but with the children being paired up with their mother, the mother may appear multiple times. So that's where you would get a one-to-many relationship. A many-to-many is actors and films. And normally this is displayed by a flat file database, which we'll look at in a second why a flat file database is not preferable. Referential integrity is another keyword. There are a lot of keywords in the database unit. Referential integrity means that no foreign key in one table can reference a non-existent record in a related table. That's a little bit of a confusing definition, but essentially what that means is referential integrity. If I needed to put in, let's say that I needed to put in the BMW, and we had a car database, and what happened is I accidentally missed out one of the letters in BMW. This has created an inconsistency, which then means that I no longer have referential integrity. Because I don't have referential integrity, that can cause issues when I'm trying to search. Because if I say that I need to display all cars that are BMWs, I put in my reports that I need to output all of the data for this, but it's not going to pick up on the values that I've spelt BMW wrong on there. So the inconsistencies can cause problems with searching, and that's why that we need to make sure that all of the data, if we are referring to something, that they are spelt the same all the way across the database. Little example here of some of the key features on there. So customer ID, sub ID, and product ID. These are unique identifiers. These are the primary keys here. You can see that the link has been created from customer ID and customer ID here. That is where we've used the primary key, and now it has become a foreign key in the subscription table. Product ID is also going to have the foreign key here. So I just wanted to show you an example of primary keys, where you've got the foreign keys, you've got creating the links between the tables there. You've also got a couple of other things in here. So we've got the field. So the fields is like customer ID, title, first name. So these are the columns, and then the records, they are the rows in there. And all of that together we've got the table, the customer table, the subscription table, and the product table. Now, with this, if I was trying to represent this in an entity relationship diagram, this is actually quite important. So a lot of people don't understand where they would need to put what's called the crow's foot. So the crow's foot is when you're drawing the entity relationship, it goes on the table. Okay. Now, a little tip to knowing how to do this is the crow's foot goes on the side where there is a foreign key. So can you see on customer ID and product ID, they are foreign keys. So that is the reason why we have put the crow's foot on there. So if you have a question in your exam and it's asking you to draw an ERD diagram, you're looking at the table, and if it has a foreign key in one of the other tables, that is where you're going to draw the crow's foot onto. In a many-to-many relationship, this would be an example here where you've got multiple entities together. We've got products, which that should be in its own table. We've got customers. It's all jumbled up, and this is generally seen as quite a bad style of database because we get repetitions of data and lots of things which aren't necessarily too good. So with all of these different questions here, one of the big things that I always see is that the answer is actually the same for all of these. So disadvantages of many-to-many relationships, disadvantages of an unnormalized database, which we're going to talk about normalization in a second, and the disadvantages of flat file databases. They all have the same disadvantages, so that this can save you a bit of time by trying to remember how to actually answer these questions. So repetition of data happens in all of these, that's a big disadvantage of these. When you have repetition of data, the follow-on point to that is that it causes data integrity issues. So when I was talking about the referential integrity, because you've got repetitions of data, that then means it's more likely that you're going to make a mistake when you're trying to enter that data into the computer, which then that means that when you're trying to search and you're trying to find things in the database, you're less likely to because of those data integrity issues. Now, we mentioned normalization. Now, normalization is essentially where we're trying to make the database more and more better designed. And we go from what's called unnormalized to first normal form, second normal form, and third normal form. The question that I've seen on this one is where they'll give you a database and they will say to you that this is unnormalized. What are the steps that you have to go through to get from unnormalized to first normal form, second normal form, or third normal form? So flashcard on each of these, this is what you need to do. First normal form is it shouldn't have any repeating attributes. So I'll show you what that looks like in a second. All attributes need to be atomic. You do not want to have full name. You want to have you want to have first name and surname. So you need to make sure that the data is all split up. So in here, what we've got here is we've got repetitions of data in there. So we've got Monday. That shouldn't, so this is an unnormalized database. This is not in first normal form. So that is a situation there which we do not want to have. So what we would need to do is we would need to start creating a link table in there so that we could start removing some of these repetitions of data. So as you can see here, we've split the entities up, and this then allows us to not get those repetitions of data. So to essentially take it from unnormalized here into normalized, and you'll be explaining this in your in the question, is I will remove repetitions of data, and I will also make sure all of the data is atomic. One of the ways that I would do this is I would create a link table, so split them up into so that there's lots of different tables, and also then I would create a link table where we've got the foreign keys there. Now, second normal form is where we remove what's called no partial dependencies, which is just where some of the data is dependent upon primary keys which aren't relevant to it. And the main way that we shift it into second normal form is all you need to say is with the link table, we use the foreign key to create a unique composite primary key. So we join those two together to create a composite primary key. Generally, because it's not going to be a massive database that's going to be in your exam question, what I would say that you need to do is to get it to go into third normal form is that you can actually probably stop there, because if you've only got to split it into 3 entities and there's only 3 entities there, and you've got a link table and you've created a composite primary key, that would also actually take it into third normal form. In a certain situation, if they did ask you what does third normal form mean, you say all attributes are dependent on the key, the whole key, and nothing but the key. And what that means is, let's say that you still split it up, and then there was one table, so that you've got the link table, you've created the composite primary key, but one of the tables actually had the instructors on there. You just need to make sure every entity has its own table. If every entity is separate, then they cannot be dependent on the primary key of something that it shouldn't be. So that there is no what's called it's dependent on the key, the whole key, and nothing but the key. So it's just those attributes are dependent upon its own primary key and nothing else. That's what that means. But the general thing I want you to go with is to go from unnormalized going into. So what you're going to do is you're going to create a link table, remove repeating data attributes, make sure that everything's atomic, create that link table. With the link table, to get it to go from first normal form into second normal form, is that you then create the composite primary key. And by that, if you've gone through and explained that process, generally, it should have gone into third normal form at that point. If you notice, though, that there is another table that you could create because you've got some instructors or whatever, that would then be how you take it from second normal form into third normal form if it isn't already there. Okay, so now we're going to move on to SQL. So SQL, the format of SQL is select from where order by. Now select is where we get the fields to be displayed. So from the database, from is the table name, where is the almost like the if statement, and then order by if you wanted to go in ascending or descending order. So this is showing you a quick example here. This table here, this is for names and breeds of female dogs. So I select name, breed. So you separate that with a comma. From dogs, so you put the table name, where gender is equal to female. And we make sure that we put that speech marks around that. Now you could put a double equal to in if statements. In SQL, just remember that you actually only put one equal sign. All of the other things are relevant though, so like greater than, equal to, less than, not equal to. that all works exactly the same, but just I thought I'd highlight that it's only one equal sign on the where statement of SQL. Now, the little star here is wildcard, which that is a shortcut for selecting everything. And then you've got from dogs where age is greater than or equal to 4. So that's that. Order by. You've got, if you need it to go in ascending order, so select star from members where num is greater than 10, order by surname. You don't need to put anything for it to go in ascending order. It will just automatically do it. But if you want it to go backwards in descending order, you need to put DESC at the end of it. So this is how you would get data from multiple tables, and you're going to use the join keyword on this one. So the join keyword, what it allows you to do is take data from multiple tables and then display it. So a couple of things which you won't be familiar with. You have to use what's called the dot notation. The dot notation is essentially where we've got like table player dot surname. So we put the table to start with, and then we have to tell it the field name that we want. So surname, first name, team name, and table.team. Then what we do is we select both tables in this case, and then this is the join keyword. So you're going to say join table player onto table team.team ID is equal to table player.team ID. And it's really, really important here that you join it based on the primary key and the foreign key. So it's the foreign key here, that's how we're creating the relationship between the two tables. So that's the one that you're going to go for on that one, and that's where you put the after the on, and then you just simply put the information in that you want it to go for. So table team dot team name equals Binham. Now, altering a table structure. So one of the things that you need to be able to do is to add a column if you want to. So alter table is the keyword on that one. Table product, add quantity and stock integer is how we would add in a new column there. Deleting or altering the table structure. So to delete a column, we go alter table dot table product drop quantity and stock. So that's going to delete a column there. To alter the table and say that we need to modify the data type on there, we're changing it into a varchar. That's going to accept essentially up to 30 values. You can put it in there like that, and you just use the modify column on there. Insert data. It's quite important on this one. So insert into, and then you put the table, put the field names, and then you just put the values. Very important that the values that you want to add in match up to the field name. So if you put A3, 4, 5, and you didn't put it in the correct data type as well, that's another thing. So if you forgot the speech marks and you put it over there, it wouldn't work. So you need to make sure it's in the correct order on those ones. Updating. What we do is you use update, set description, and whatever the things that you want to change. And then you just have to identify it normally by the primary key. So that's going to be there. Deleting a record, delete from product where product ID. So using the primary key to help you do that. Now, this is just going to be relevant for the OCR specification. So the ACID principle is atomicity, consistency, isolation, and durability. So it's this idea of that we've got certain properties that are going to ensure the integrity of the database is maintained under all circumstances. And what you need to know for the exam is like what each the A, the C, I, and D all mean. So if we just go through and do those, you can just make a flashcard on each of those, remember the definitions, and then you'll be able to get some marks on those ones. So atomicity, it has to. So if we've got a transaction or we're trying to put something into a database, it has to be processed in its entirety or not at all. So let's say it crashes, you can't process part of the transaction. Consistency, that no transaction can violate any of the defined validation rules. So and this is going to help us with referential integrity. So again, just making sure that your database is consistent with all of the data that we're inputting. Isolation ensures that concurrent execution of transaction leads to the same result as if transactions were processed one after each other. So it's just just going through and making sure that everything is processed, and we're going to get the same result in that regard. And then also durability, so ensures that once a transaction has been committed, it will remain so even in the event of a power cut. As each part of a transaction is completed, it is held in a buffer or on a disk until all of the elements of the transaction are completed. Only then will the changes of the database tables be made. So once everything's finished, then it's going to process the actual changes to the database. Now, that's good. That's all we've got for today, people. So I really hope that everything goes well. I'll try my best to get the OOP lesson out for you tomorrow as well. So best of luck. Hope everything goes well, and all the best.